Hello everyone, welcome back to the class. Today we will hold the last lecture in module 10, and in this last lecture we will talk about different techniques for producing polarized light. Now, in this direction we will first talk about the wire grid polarizer, and then we will also talk about polaroid. This is a technique wherein a polarized light is produced using a very thin and long conducting wires. Now, this wire grid polarizer essentially consists of a large number of thin wires, and these wires are placed parallel to each other. Now, suppose these are the wires which are very closely spaced. On these wire we launch an unpolarized light. Okay, and what happens is that now since these are the wires and unpolarized light impinge on it, then the component of the field which is along the length of the wire, what will it do is that it will make the electron oscillate, and due to this electric field does work on the electron inside this thin wire, and the energy associated with the electric field is lost in the Joule heating of the wires. Okay. And this is how the component which is parallel to the length of the wire, it get consumed, it get absorbed, and what is left is the perpendicular component, and this is how we get a linearly polarized light using this wire gate polarizer. Okay. On the other side we will get a linearly polarized light. As I said before, not all horizontal components are absorbed, or it is not only that only vertical components are coming out of the wire grid polarizer. A component which is not perfectly vertical, they also come out, but the dominance is of vertical component. Okay. Therefore, we call it a vertically polarized or linearly polarized light. Now, on the other hand, since the wires are assumed to be very thin, the component of electric field vector along the x axis passes through without much attenuation. Okay. The x axis is vertical axis. Okay. Thus, the emergent wave is linearly polarized with the electric vector along the x axis, and this is very nicely depicted in this figure number 14. But we know that spacing between the wires should be either equal to lambda or much less than lambda. The spacing between the wire must be smaller than the wavelength of the light. Okay. But this is not feasible because wavelength of light is very small. And how to achieve this wire grid polarizer? Now, instead of this thin wire, one may employ long chain polymer molecules that contains atoms which provide high conductivity. Okay. If we take polymer molecules which are very, of course, very thin and very much conducting, such as iodine, then this wire grid polarizer can be replaced with this long chain polymer molecule, and this long chain polymer molecules are aligned so that they are almost parallel to each other. Okay. A sheet containing such long chain polymer molecules which are aligned parallel to one another is known as polaroid. Okay. And when light is shined over such a polaroid, then the parallel component of the field get absorbed while the perpendicular component is passed through, it get transmitted. Okay. And this is how we get a linearly polarized light out of a polaroid. Now, the second technique to produce polarized light is polarization by reflection. Okay. In this case we use Brewster's law. Okay. Here we assume that unpolarized plane wave is incident on a dielectric. Okay. And we also assume that the electric field vector associated with the incident wave lies in the plane of the incidence. Okay. And if the angle of incidence is equal to theta p or theta b, the Brewster angle, which is equal to tan inverse n2 by n1, where n2 is the refractive index of the medium, the second medium, and n1 is the refractive index of the first medium, then in this case we get no reflection, okay, because we have already studied that in if the angle of incidence is such that it is equal to Brewster angle, then for in plane polarization the reflection is absent. All the energy would be in the transmitted arm of the propagation. Okay. But if an unpolarized beam is incident at this angle, then the reflected beam will be linearly polarized and with its electric vector perpendicular to the plane of the incidence. Yeah. Now, here in this case we say that we are launching an unpolarized light which has perpendicular component as well as parallel component. In this case, in the reflected arm there will not be any parallel component, but only perpendicular component, while the transmitted arm will have both parallel as well as perpendicular component, and this transmitted arm is called partially polarized because most of the perpendicular component is there in the reflected arm. But if we use stack of material, in this case air glass, if we take such periodic arrangement, then due to multiple reflection and refraction, ultimately we get almost polarized light here at the output, at the transmitted end. Now, let us consider the case of air glass interface, and suppose the unpolarized light is falling at the glass interface from air. Therefore, in this case n1 would be equal to 1 while n2 would be 1.5, and using these two values we can calculate the Brewster angle theta b, which is 57 degree. The transmitted beam is partially polarized, and if one uses a large number of reflecting surfaces, one obtain an almost plane polarized transmitted beam. Okay. Now, instead of air glass interface, if we consider air water interface where n1 is equal to 1 and n2 is equal to 1.33, then the polarizing angle or the Brewster angle would be 53 degree. Okay. And thus, if the sunlight is incident on the sea, which is of course water, at an angle close to the polarizing angle, then the reflected light will be almost polarized. And now, if you use a rotating polaroid, then the sea will appear more transparent when the polaroid blocks the reflected light. Okay. And this polaroid, this phenomena is used in sunglasses. Now, in this line, the third method to get polarized light is polarization by double refraction. Here we use birefringent material, and we know that when unpolarized light is incident in an isotropic crystal or in a birefringent material, then it splits up into two beams, okay, each being characterized by a certain state of polarization. Okay. Now, these two beam, they both are linearly polarized, and if we want only one beam to come out somehow from the material system, then we will have to devise the technique to eliminate one of the beam. Okay. If we eliminate the one, then the other one, which is a linearly polarized wave, we will be left with the other one, which would be a linearly polarized wave or linearly polarized beam. Now, how to do this? A simple method for eliminating one of the beam is through selective absorption, and this process of selective absorption is known as dichroism. Okay. There are few certain crystals, and one of the example is tourmaline, and this crystal has different absorption coefficients for different polarization. Okay. Now, suppose we launch unpolarized beam in this crystal, and due to its birefringent nature, it splits the unpolarized light into two beams, and one is in plane polarized, other is perpendicularly polarized. And if there is a polarization dependent absorption, then one of the beam would be absorbed and we would be left with the other beam, which is also a linearly polarized beam, and we will get only one linearly polarized output through this tourmaline crystal, which is schematically drawn here. You see here, in this crystal we launch an unpolarized light, and this unpolarized light splits into two. One has polarization direction, which is in vertical direction. Yeah, one beam is vibrating in a vertical direction, while the other is vibrating in a horizontal direction. The properties of the crystal is such that this horizontal vibration is absorbed with propagation. Okay, it absorbed very rapidly, while the other beam, which has polarization direction in the vertical direction, the vibration is in vertical direction, it sees a small value of attenuation, and therefore, it comes out of the crystal and we get a linearly polarized light at the output. Now, another method for eliminating one of the polarized beam is through total internal reflection. Now, what do we do here is that since the two beams has different velocities, and as such the corresponding refractive indices will be different therefore. Okay. Now, if one can sandwich a layer of material whose refractive index lies between the two, we launched an unpolarized light in a birefringent material and then it splits into two. The two rays are named as E ray and O ray, and the two rays have different indices of refraction. Now, if we put a material whose refractive index is between that of NO and NE, or that of E ray and O ray, then the material which is put externally, it will behave as a rarer medium for one beam while denser medium for the other. Now, using this principle, we can form a crystal wherein one ray falls at an angle which is larger than critical angle. Okay, and if the angle of incidence is larger than the critical angle, then out of the two rays, one ray will be reflected, totally internally reflected, and we will be left with the other ray, which is again linearly polarized. Okay. And this principle is used in the Nicol prism, which consists of a calcite crystal cut in such a way that one beam for which sandwich material is rarer medium, the angle of incidence is greater than the critical angle. Thus, this particular beam will be eliminated by total internal reflection, and this tourmaline crystal is shown schematically here. Okay. And this shows the properly cut calcite crystal, and here at this along this line a layer of Canada balsam is introduced, and the ordinary ray undergoes total internal reflection at this Canada balsam layer. Okay, you say that we are launching unpolarized light and the O ray get totally internally reflected, while the E rays passes through as it is. Okay. The E ray component passes through and the beam emerging from the crystal thus is linearly polarized. Here we get a linear polarized light at the output, while here we have launched an unpolarized light. Okay. Now, the fourth method of producing polarized light is polarization by scattering. We know that if we have a dipole, say it is a plus sign and it is a minus sign, and these point charges are separated by a certain distance d, and if we somehow make this dipole oscillate with certain frequency, then we know that oscillating dipole emit electromagnetic radiation, and the radiation pattern would be in the form of butterfly wings, and therefore, the pattern emitted would be in this form. Okay. And this would be the direction of emission. These lines represents, arrows represent the direction of emission of electromagnetic wave. Now, you see that the dominant emission is perpendicular to the length of the dipole. Okay. This is the direction of dominant emission, this horizontal arrow, thick horizontal arrow, and this is perpendicular to the length of the dipole. Okay. Therefore, if a dipole vibrate, the emission is perpendicular to the direction of vibration. Okay. Now, using this we can also create polarized light. How? If an unpolarized beam is allowed to fall on a gas, okay, and gas consists of several molecules, yeah, which are well separated from each other. Now, if unpolarized light is launched in this gas, then the beam scattered at 90 degree to the incident beam is linearly polarized, yeah, and this can be again understood from this figure. Suppose we launched an unpolarized light on this dipole, then out of the n number of direction of vibration, the field which is the field component which is along the length of the dipole, I mean this field component which is along the length of the dipole, this field component which is function of time, it will make the dipole oscillate, and therefore, it will get absorbed into the dipole, and after the absorption the dipole will radiate in this direction, and this emission would be in perpendicular to the vibration of initial field. Okay. Therefore, the incident beam is scattered at 90 degree to the incident beam, and this would be linearly polarized. This follows from the fact that the wave propagating in y direction are produced by x component of the dipole oscillations. The y component of the dipole oscillation will produce no field in the y direction. Okay. If the incident beam is linearly polarized with its electric vector along x direction, then there will be no scattered light along x direction, and this is schematically shown here. Now, this is our scatterer or the gas molecule on which we are launching an unpolarized light. Now, in x direction we will receive a light which would be y polarized, while in y direction we will receive a light which would be x polarized. Okay. Now, suppose we have a scatterer on which we have launched a x polarized light. Now, due to the x polarization, the dipole will vibrate in this vertical direction. Okay, the vibration would be like this, and due to this vibration the emission would be in y direction, and this emission would be x polarized. Okay. Now, these were the few methods to generate polarized light. Now, in this method we have also talked about polarization produced by birefringent material or double refracting material. Now, using these birefringent material we can devise a different type of devices, and one of such devices Wollaston prism. Okay. A Wollaston prism is used to produce two linearly polarized beams, and it consists of two prisms, two similar prisms with optic axis of the first prism parallel to the surface and the optic axis of the second prism parallel to the edge of the prism, and this is shown here in this figure. Okay, you see that this is the Wollaston prism consists of two prisms. This is the first one and this is our second one. In first one the optic axis is along this line, while in the second one the optic axis is perpendicular to the plane of the paper, and the direction of the optic axis is shown by these dots. Okay. Now, if you launch a ray whose direction of polarization is perpendicular to the plane of the paper, then for the first prism, this is our first prism, this ray will behave as a O ray. Why? Because in the first, for the first prism, the D of the incident beam is perpendicular to optic axis, and since this is direction of propagation k, D is also perpendicular to k, and therefore, the incident beam will behave as a O ray in the first prism, and therefore, since the incidence is normal, it will propagate undeviated. Now, at the interface of second prism, we will have to draw a normal and we will check the refraction of this O ray. Now, in the second medium, the vibration, the D in the second prism, the vibration direction is not perpendicular to OA, although D is perpendicular to K. Okay. D is perpendicular to K, but D is not perpendicular to OA. Instead, D is in a plane which contains both OA and K. Therefore, the same ray in the second prism, it will behave as E ray. Therefore, for refraction, we will use NE as a refractive index for the same ray in the second prism. Okay. And using this NO and NE, we can calculate the angle of emergence, that is theta 1 out of the prism. Okay. Therefore, if we launch a beam with a polarization which is perpendicular to the plane of the paper, it will emerge out at angle theta 1 in this direction, while launch a ray whose polarization is in the plane of this paper, then this ray will behave as a E ray in the first prism, while O ray in the second prism. Okay. Now, and this the direction of emergence would be different, it would emerge at an angle theta 2, the opposite direction. Therefore, if we launch an unpolarized light in such a prism, then the perpendicularly polarized beam will emerge from here at angle theta 1, while in plane polarization will emerge at angle theta 2 in the other direction. Okay. And therefore, using this Wollaston prism, we can generate two linearly polarized beams from an unpolarized light. Similarly, there is another prism which is called Rochon prism. The Rochon prism consists of two similar prisms. The optic axis of the first prism is normal to the face of the prism, while the optic axis of the second prism is parallel to the edge of the prism, as shown here in this figure. Okay, here this is the optic axis of the first prism, while this is the direction of optic axis of the second prism. Now, here again if you launch an unpolarized light, the in plane polarization component will go straight and the perpendicular polarization beam will go in the other direction, and which will emerge out at angle theta with respect to the horizontal. Okay. Now, if the prism angle is 25 degree, for here you can easily calculate this deviation, this angle of deviation theta. What you will have to do is that we are launching an unpolarized light. Okay. Now, therefore, we can use Snell's law, and it says that NO sin I, which is 25 degree, is equal to NE sin R. Okay. With this we can calculate the angle of refraction. Okay. Now, here this polarization, the dot polarization, you can see the dot polarization is perpendicular to the optic axis of the first prism, and it is also perpendicular to the direction of propagation. Therefore, this dot polarization work as a O ray in the first prism, while this plane polarization, this in plane polarization, it is perpendicular to the optic axis and as well as it is perpendicular to the direction of propagation K. Okay. Therefore, you can also say that it is working as a O ray, but the K vector is in this direction and optic axis is also in this direction, and therefore, you can see that you cannot create a plane out of it. Therefore, both of these polarization will work as a O ray. Okay. Now, once NE is given using this Snell's law, we can calculate the angle of refraction, and once angle of refraction is calculated and you know this slanted plane is making an angle of 25 degree with the vertical, the angle of incidence at the second interface would be 3.2 degree, and from here angle of emergence can easily be calculated using again Snell's law, which is given by this relation. Okay. Now, with this I end this lecture, and thank you for joining me. See you in the next class.